Okay, so we're going to look at reactions as part of our review of statics. And because this is one of the first example problems that we'll do as a part of the course, is I'll probably talk a little bit more at depth as to what I think goes into properly laying out a solution to an engineering problem. A little bit right from the mundane, if you will. Of course, we should always have our name at the top of the page. So I'll put it up here. I'll just use my initials just to keep it short, but we should have our name. And to be fair, you should probably also identify how many pages and what page this is. And I'm sure we can wrap this up in a single page. So the problem itself says to find the reactions at A and B. And so our step along the path in order to do that is to do the free body diagram. So we should always label what we're doing. So we can call it free body diagram. Of course, as you'll see in many of my later videos, I just call it a free body diagram, FBD. It's something we use all the time. So one of the techniques that I've developed over the years, not saying that it's what you have to do or should do or anything else, but one that I find is both efficient and clear, is that typically if I'm dealing with a beam or something like that, is I extend the geometry of the beam down by just these lines, and that basically allows us to carry on the dimensioning in our free body diagram and other diagrams we might want to do later on without having to repeat them. Because otherwise, quite frankly, if you do it completely independently, it should include all of your dimensions and everything else. But because of the way I do it, you'll see I don't repeat the dimensions because they are implied by the way this lines up with our original problem. So we have a clear statement of the problem, and we're ready to start our free body diagram. So the first thing we do is we draw out the structure using centerline lines. So we don't give it thickness, if you will. So this beam has a thickness, but we're just going to draw a straight line to reflect the beam itself. So let me just do that here. Okay, so I've drawn in a line to represent the beam. And now what we have to do is we have to record all of the external loads being applied. So I'll just draw in P at the center span here. And our reactions. So we would do reactions at A. Now this is a pin, so it would have two reactions or two components of force. So we have an X component and a Y component. We'll break it up into those. So we'll do our reaction at A in the Y direction, reaction at A in the X direction, and our reaction at B in the Y direction, only one because that's a roller, so it doesn't have a horizontal component of resistance. And the other thing that we should do if we're being complete is we should indicate our necessary axes, X, sometimes a Y, sometimes a Z, depending on what the problem is. So I will just indicate an X and a Y directions in this case. And with the dimensions implied from above, that really completes our free body diagram. So to get to our reactions, then we need to apply our equations of static equilibrium. And good note keeping, we should always not we should never leave our checker guessing to wonder what it is that we're doing. So we should always annotate our solutions as we go along. So in this case, I'm just going to say apply equations of static equilibrium, and I'll underline that just so I can stand out. And the first one that I'm going to apply in this case I normally like to try to start with one of my moments because if I choose the location about where to calculate my moments, I can usually get rid of a couple unknowns because where the line of action passes through that point, of course, there is no perpendicular distance to them so that they go to zero, and that leaves us typically with one equation and one unknown, and I can avoid back substitutions. So I'm going to go ahead, and in this case, I'm going to choose to do the sum of the moments about A because it has two unknowns with line of action through A, RAX and RAY, and set that equal to 0. I'm going to identify that I'm going to do moments clockwise as positive. So if the force that we're considering is trying to turn the structure clockwise about our point of consideration, in this case A, then we would write it in as positive. If it's trying to turn it counterclockwise, then we would give it a negative sign. So we have two forces to consider in this case. So the first one being P. So P is, if we consider kind of putting a pivot at point A, P is trying to turn our structure clockwise about that point, so it would be positive. So we'll put it in here as P, and that's multiplied by its perpendicular distance, which in this case is equal to L over 2. And the only other force that we have contributing to moments about A would be RBY, and it is based on the way we've drawn it anyway, turning it counterclockwise. So we will put that in as a negative RBY and multiplied by its perpendicular distance, or moment arm, which in this case is equal to L. So we can simplify that, go through some algebra. Ultimately, that allows us to come down to RBY is equal to P over 2. So we have two other equations of static equilibrium. So let's do sum of the forces in the y direction. Set that equal to 0. In this case, I'm just going to choose up as positive. And so we have three forces acting in the y direction. We have RAY, we have P, but it's acting down, so I'll put it in as a negative P. And then we have RBY, which is positive. Now, in this case, we already have a solution for RBY, which is P over 2. And so we can substitute that back in there. And that means we only have one unknown, RAY, and we determine that it also is equal to P over 2. So to be complete, the last equation of static equilibrium that we have is sum of the forces in the x direction equal to 0. I'll do positive x as positive, and that would be equal to RAX. Because there are no other applied forces going in the x direction, as no surprise, RAX will be equal to 0. So as good note taking and everything else, I do like to highlight those answers that are asked for in my solution. So I typically put a box or underline them. Helps if it's red so that they're easily identifiable. These are all really up to you to figure out what you're going to use. The only thing that I would say is that you shouldn't leave people looking and you shouldn't leave people guessing. How you do that is really up to you. So here we go. Our three answers clearly understood. Depending on your professor and or your requirement for your reporting and stuff like that, it would not be uncommon to do a summary of results. A little bit trite in this point because it's such a simple solution. In that case, I would probably simply write down RAX is equal to 0, RAY is equal to RBY is equal to P over 2. And with that, we have a fairly logical, well laid out solution to this problem. The actual application of statics, fairly easy to do in this case, but also a couple tricks as to what order to do them in, making sure that you identify your positive direction, that type of thing. And of course, if any of our answers had come out negative, all that means is that the direction that we had drawn it in the first place, which was fundamentally an assumption, just would have been reversed, and it would have been going down, say, instead of going up. But otherwise, that pretty much sums this up. We'll be following on with our next example in this series, and I'll just try to put a link to it right here at the end so that you can watch them one after another if that's what your workflow requires.